You ever been looking at the specs for some new piece of gear, maybe a power tool or even something for your car, and you see it, this little code like G2.5 or G6.3, just kind of tucked away in the details? And you probably just blew right past it, right? Well, what if I told you that little G is actually the secret key to understanding pretty much everything about that machine's performance, its lifespan, and even how loud it's going to be? So, what's the deal with these codes? I mean, G2.5, G6.3, G40, they're not just some random model numbers. They're actually part of a secret language, a universal code that engineers all over the world use to talk about one of the most basic forces in all of mechanics. And today, yeah, we're going to crack that code. At the end of the day, it all comes down to one thing: controlling vibration. Just think about a washing machine when it hits that final spin cycle and the clothes are all bunched up on one side. You know that violent, house-shaking wobble, that insane noise? That is the raw, destructive power of imbalance. Now just imagine that same force, but inside a high-speed engine or a precision grinder. It's not just annoying anymore, it's catastrophic. Okay, so how in the world do you measure and control an invisible force like that? Well, that brings us right to the code itself. So let's jump into our first section here, decoding the greed grade. First thing you need to know is this isn't just some made-up number from a single company. Nope, this is a formal international standard, ISO 2194011 to be exact. It's officially called the Balance Quality Grade, and it's basically the global language for saying exactly how perfectly balanced any spinning part, what engineers call a rotor, needs to be. And the idea behind it is actually beautiful in its simplicity. That number after the G, that's a direct measurement. It's the absolute maximum vibration speed allowed in millimeters per second. So if something has a G6.3 rating, it means that when that part is spinning, its center of mass can't be wobbling around any faster than 6.3 millimeters per second. Simple, right? The lower the G number, the smoother it runs. So how do they even calculate that grade? Well, the math is actually kind of cool. It all boils down to two key things. First, how much the part physically wobbles. How far its actual center of mass is from its perfect geometric center. And second, how fast it spins. You just multiply those two things together, and bam, that's your G grade. It's this perfect, direct link between a physical flaw and how it's actually going to perform in the real world. So let's see how this all plays out, because obviously a car tire doesn't need to be as perfectly stable as, say, a gyroscope in a satellite. And that brings us to the full spectrum of precision. And this table just lays it all out perfectly. Way up at the top, you've got the rougher grades like G40 for car crankshafts or G16 for big heavy-duty parts on farm equipment. Then, as you go down and the numbers get smaller, the jobs get way more demanding. G6.3, that's your sweet spot for things like commercial jet engines and big industrial fans. G2.5 is super common for high-speed motors and machine tool spindles. And then you get to the really wild stuff, the elite levels, G1.0 and G.4. That's reserved for things like gyroscopes and ultra-precision grinders, where even the tiniest vibration means total failure. Let's just really hammer this home by looking at the two extremes. On one hand, you have a G40 crankshaft. It's built for raw, brute force. A little bit of vibration is just part of the deal. But a G0.4 gyroscope, that needs ultimate, absolute stability. Any detectable wobble would completely destroy its measurements. The level of engineering and pure manufacturing perfection you need to hit G0.4, it is on a completely different planet from a G40. Okay, now we're getting to what I think is the most fascinating, most critical part of this whole topic. Because it's not just about how physically balanced an object is, it's all about the dance between its speed and its balance. So this leads to a really interesting question. Let's say you have two different parts, and they both have the exact same G2.5 rating. Does that mean they are physically balanced to the same level? Do they have the same amount of actual physical wobble? And the answer is a huge, definite no. And if you take away one thing from this, let it be this. To get the same G grade, a part that spins way, way faster has to be physically more perfect. It needs to be balanced to a much, much higher standard. Okay, let's just stick with that G2.5 example. This chart makes it crystal clear. A motor that's spinning pretty slow can hit that G2.5 grade even if it has a relatively high amount of physical imbalance, a wobble you could probably see.
But for a super high RPM spindle to get that exact same G2.5 rating, its physical imbalance has to be microscopic, almost non-existent. Why? Because at crazy high speeds, even a tiny, tiny flaw gets amplified into this massive destructive force. Speed demands perfection. So, what does this all mean in the real world? Well, it leads us to a really important principle in engineering. It proves that the goal isn't always just chasing the smallest number, the best spec. It's about finding what's appropriate, which is about more than just being the best. You see, picking a right G grade is a true balancing act. It's a constant trade-off. On one hand, yeah, a better balance, a lower G number means less wear and tear on bearings and parts, so the machine lasts longer. And of course, it runs smoother and quieter. But, and this is a huge but, achieving that insane level of precision is incredibly expensive. We're talking specialized machinery, more time, more quality control. The cost skyrockets.
And that brings us right to the punchline, the key takeaway of this whole thing. It is a fundamental rule of engineering that goes way beyond just spinning parts. The goal isn't always the highest precision. It's the right precision for the job. I mean, engineering a G0.4 balance for your car tires would be a technical marvel, sure, but it would also be completely absurd, insanely expensive, and totally unnecessary. So, the next time you see that little G code on a spec sheet, you won't just skip past it. You'll see the story behind it, a story of trade-offs, of careful engineering choices. And that leaves us with one final thought. As you look at all the technology around you, everything from the fan in your laptop to a giant wind turbine, can you start to see where the engineers found that perfect hidden balance between precision and price?